Welcome to the 2021 Materials Research Society Fall Meeting. The Fall Meeting events continue virtually this week with more great symposium sessions, keynotes, and award talks, and much more. This is MRS TV. Welcome to the first episode of MRS's virtual component of the 2021 Fall Meeting. We are glad that you've joined us. On today's episode, we catch up with a few great guests virtually and from the events happening in Boston. And we'll take a look back at the innovative research centers across the world that are discovering the materials needed for the technologies of tomorrow.
MRS TV welcomes Nicholas Kotov, recipient of the 2021 David Turnbull Lectureship Award. Well, thank you so much for joining us today, Nicholas, and congratulations on your award.
Thank you, Stacy. It's a pleasure and a great honor.
So your award reads for foundational discoveries in interface-based engineering of self-organizing materials. Tell us about your work and how you came to the study of this particular field of materials in your research.
The typical materials, polymers, semiconductor metals, are created considering their chemical structure in the bulk. And often interfaces there between domains, between crystallites, are considered to be flaws. And some time ago, in late 90s, we have realized that interfaces are not flaws. They're a rich source of chemical structures which are impossible to obtain in any other way. These new chemical structures which are created at interfaces can be utilized to engineer marvelous new properties for materials. And we have demonstrated that for the two-dimensional material of alumosilicate, the platelets of clay, and build up the layered structure with a large contribution of interfaces. But even more so, interfaces is a platform for the realization of self-assembly, as you mentioned.
So your lecture is titled Nanoscale Biomimetics from Self-Assembled Nanocomposites to Chiral Nanostructures. Can you give us a preview of that talk?
We learn from nature, and we kind of think about nature as the ultimate in complexity, as it can create very sophisticated geometries, very sophisticated materials arrangements, and dynamic structures. What we also learned in the latest work by introducing chiral nanoscale structures and chiral platelets, that not only we can match nature in the sophistication of the geometries and in hierarchy, but we can also exceed it. First, we replicate how nature does it, and then we do it better, and then we obtain even better and better properties.
Your bio describes you as a passionate advocate for scientists with disabilities. Are individuals with disabilities overlooked when considering diversity? Tell us about your work in that area.
Thank you, Stacy, for asking this question. It is an incredibly important topic. It's very close to me and to a lot of other scientists. I think we need to ingrain the message that our ability to be good scientists, materials engineers, and good people is totally independent what ethnic origin or what kind of abilities we have. And I think we need to strengthen this message, in particularly at MRS. I met recently a young man, and he was in a wheelchair, and he was interviewing for the faculty positions. And I asked him, why you're not submitting your applications to University of Michigan? And he says, I don't think you would be interested in me. And I tried to assure him that it's not right. And it is an example how we overlook some of those people who are very able and very intelligent, but have something that they're afraid of. And I think we need to change that.
Well, thank you so much for joining us, Nicholas, and I hope you have a good rest of your day.
Thank you, Stacy.
And now to the first of our visits to labs around the world. It's the Research Institute for Intelligent Wearable Systems at the Hong Kong Polytechnic University.
The Research Institute for Intelligent Wearable Systems is to conduct interdisciplinary research to advance knowledge and create new technology, then transfer this technology to industry to help the development of new knowledge-based industry in Hong Kong and beyond. We have 3 areas of research: high-performance materials and devices that's suitable for wearables, to develop scalable processing technologies for fabricating devices and system integration, to apply these systems into different fields like health, sports, fashion, entertainment, and safety. We have developed technologies to use the existing machinery and process, modify them to make the finest electronic yarn, where the microelectronic chips are embedded in textile yarn. Then you can knit this yarn or embroider this yarn into fabrics to make devices and a system.
NV microscopy is a recent development that has extended nanometer imaging and analysis into the world of magnetic fields, currents, electric fields, and noise. Let's take a look at how Qsaber are making these microscopy tools more accessible.
So at Qsaber we try to get the most out of a scanning NV system by enhancing the performance of each individual part for characterizing surfaces at the nanometer scale.
The scanning tip is important for the measurements because it contains the NV center, which is our field probe. Furthermore, the nanopillar structure in the diamond helps to improve collection efficiency so that we can collect more of the NV center fluorescence.
Another unique feature of the QSM is really the optic set. We have put a lot of engineering and thoughts into designing custom optical elements that immediately impacts the signal to noise, that translates into better data quality and faster measurement time.
When using pulsed protocols, you gain sensitivity because you reduce effects such as power broadening when you use continuous wave experiments.
The most important results in the past year or two have been made with antiferromagnetic materials. And we're also looking in other imaging modalities. So the idea of this instrument will be to do correlated imaging of electric fields, magnetic fields, and maybe optical properties.
Now we would like to welcome Emily Carter of UCLA. Emily, thanks so much for joining us today.
Oh, it's my pleasure.
Congratulations, Emily, on having been named the recipient of the 2021 MRS Materials Theory Award. Now, you will be presenting a talk during the Lightning Talk session during the virtual meeting titled Quantum-Derived Materials, Solutions for a Sustainable Future. Can you give us a preview of what you'll be discussing?
Well, it's only a 7-minute talk, so that was quite a challenge to select. So what I'll be doing is starting with a brief overview of in my group, what we have been doing for decades is developing quantum-based simulation techniques. So we develop and we apply those of others to a wide variety of phenomena involving molecules and materials.
Now let's focus on that sustainable future portion of your talk title. So many of the presentations at this meeting have a sustainability focus. How does your work fit into the overall concept of sustainability?
We've been working quite some time on different materials discovery through quantum-based simulations. Basically characterization of known materials, which then lead us to understand their properties and be able to come up with key concepts for optimizing better materials for sustainable energy technologies that convert sunlight into electricity, or that convert sunlight and chemicals into other chemicals and fuels. And so that's been a large part of the work that I have done over the last 15 years. And I'm going to give in my talk a couple of examples related, more recent examples related to electrochemistry, materials for electrocatalysis and materials for a certain kind of photocatalysis.
Let's talk a little bit about your career path. What led to your studying this particular field of materials science, quantum mechanics, and simulation?
Well, I have to say that as an undergraduate at UC Berkeley, I fell in love with physical chemistry and quantum mechanics, and it's the case that little did I know that being a physical chemist and getting a PhD in physical chemistry and theoretical physical chemistry at Caltech would essentially be terrific training in many ways. So that's what led me initially, and then. As a graduate student, discovered that one could develop and apply quantum mechanics methods to really extract very important, powerful concepts that could lead one to understanding all sorts of phenomena.
And what are some of the near-term things that you'll be working on in your lab, and what are some of the longer-term issues to be discovered in this field?
I have decided at this point that my current and future research efforts are really all about carbon mitigation and in particular converting carbon dioxide and methane. And so doing a lot of work on essentially characterization and materials discovery for efficient ways to essentially to utilize carbon dioxide and methane, not just try to store it or burn it in the case of methane, but also to actually utilize it and hopefully have it be not just there be economic drivers, but also have there be ways of sequestering it with an economic driver that makes sense.
Well, once again, Emily, thank you so much for your time today. We certainly appreciate it.
Oh, well, thank you very much. It was lovely to talk with you.
And now to KAUST, Organic Bioelectronics Laboratory, where researchers are developing organic electronic materials that interface with living systems.
Making electronic devices for biological systems is very challenging. Electronics just simply do not understand what living systems are trying to say, or it becomes very difficult to make living systems to respond to electronic cues. My lab deals with organic electronic devices and their applications at the interface with living systems.
Once we established the ability of materials to translate signals, we use them to fabricate our own devices.
One of our favorite devices is the organic electrochemical transistor. These devices allows us to benchmark the transport properties of the polymers we study.
The OECG is interfacing directly with living cells. We can visualize non-invasively the growth of the cell during a long period of time.
One of the most timely contributions of our lab is the coronavirus sensor.
We are very excited to contribute to the well-being of millions of people worldwide.
As we continue to advance information technology systems faster, more energy-efficient materials will be needed. The Institute on Functional Oxides for Energy-Efficient IT is working to help solve this challenge with their research on thin-film metal oxides.
In the Institute on Functional Oxides for Energy-Efficient IT, we focus on quantum and neuromorphic materials. Our vision is to address grand challenges in the field of information technology that target low energy consumption.
So here we are at the Molecular Beam Epitaxy laboratory. This allows us to grow epitaxial ultra-thin films.
To understand and optimize the physical properties of our materials, we use Raman spectroscopy, spectroscopic ellipsometry, XPS, electron microscopies, and scanning probe microscopies.
At iFox, we developed device concept based on our material growth expertise and physical insight that we gain with extensive characterization. All these devices are developed with an aim to integrate with silicon CMOS chips for neuromorphic computing.
iFox gives an excellent opportunity to expand my knowledge on a broad spectrum.
By creating the next generation of materials, we aim at a more sustainable future.
MRS TV welcomes Yuri Gagatzi of Drexel University. He's here to discuss his award-winning MRS work. Well, thank you so much for joining us.
My pleasure.
And congratulations on having been named the 2021 recipient of the MRS medal.
Thank you.
So the world of MXenes has been growing greatly. What are some things that have led to these breakthroughs?
Well, one of the things that is important to understand, this is not just another two-dimensional material like graphene or moly disulfide. This is a totally different materials world because we can control the number of layers of transition metals in carbides and nitrides. We can control ordering of these layers. We can have in-plane and out-of-plane ordering of elements, and we can control surface terminations. If you go just with the currently known compositions, at least 100 of stoichiometric structures possible, at least 1,000 if you count surface terminations. We're really talking about redesigning the materials world with this family here. And that's why there is such an enormous interest and such a fast growth of research in the field of MXenes.
So what do these discoveries mean in terms of application and products?
So we look at this as building blocks of the future world, these materials. We're making just the first baby steps, but they already are being explored in energy storage, but also medicine. Healing, for example, cancer cells by illumination with red light. They are used for dialysis, and there is a company launched to commercialize this application to extend life of patients who suffer from acute kidney disease. They are used for optoelectronic applications. Antennas, communications, lasers, electromagnetic interference shielding. So pretty much because of this very large number of materials and very wide range of properties, there are probably no area of human activities where MXene won't be able to eventually find applications. Whether they will appear to be the best material for this application, this is what I think the research community will be exploring over the next decades.
Wow, that's awesome. Well, thank you so much, Yuri Gagatzi, for joining us today, and congratulations on your award.
Thank you. And also, just to mention at the end, there will be an entire MXene symposium at the spring MRS meeting. And I would like to invite everyone to join this symposium in Honolulu, in Hawaii.
We can't wait. Thank you so much.
Artificial intelligence is changing the way researchers tackle a variety of challenges in the lab. Let's see how the Advanced Materials Research Facility in Mississauga, Canada, is building a team of collaborators to use novel tools such as AI to help Canada meet its emissions reduction goals.
An Advanced Materials Research Facility has been built to develop clean energy solutions to help Canada meet its emission reduction targets.
We host a new initiative jointly led by the National Research Council of Canada and Natural Resources Canada, which is a first initiative of its kind in the Greater Toronto Area.
Our 4 research pillars include accelerated materials discovery, materials for electrocatalysis, powder synthesis, and smart materials for smart objects.
We bring collaborators together to share resources, pool our knowledge, and shape new scientific directions.
We're forming close ties with the University of Toronto's Acceleration Consortium.
It's called consortium because we bring together academic researchers, industrial researchers, and government researchers.
Let's consolidate our expertise and accelerate research to address challenges that impact the global community now.
And now to Singapore, where the Accelerated Materials Development for Manufacturing Research Program is using new computing tools like machine learning to accelerate materials development.
The next frontier really is in the use of robotics and automation for high-throughput workflows, both in experiments and in theory, coupled with machine learning and optimization to accelerate materials research. So this really was the essence of the AMDM program. So this brings together A-star research institutes focusing on materials research, machine learning and applications, as well as the 2 local universities in Singapore, National University of Singapore, NUS, and Nanyang Technological University, NTU. If you really want to accelerate materials research, our tools can help you augment the speed at which you do the research. The tools that we make available hopefully will be open source, should have data provided to everybody, It should be easy to use. We have startups coming out of our program, for example, that use these tools. We have applications where we actually help multinational corporations accelerate their workflows. We actually have small, medium enterprises who do not know how to collect data efficiently, and our tools help them to sample the parameter space more efficiently. So the vision really is to provide tools to the global community of research so that we can accelerate materials research everywhere.
And that's all for this 4th episode of MRS TV. Make sure to join us tomorrow for our final show and a conversation with Dr. Juji Chen on the synthesis of porous crystalline materials, and Stafford Sheehan, who will discuss how his company converts carbon dioxide into alcohols. Thanks again for joining us, and don't forget, you can always find us on the meeting homepage as well as online. See you next time.
MRS now offers a free 1-year dues renewal option for recent doctoral graduates. This offer, available only once per member, is designed to support our next generation of researchers as they transition from student to career professionals, and will include all benefits and advantages of MRS membership. The next membership cycle begins January 1. Check your inbox. Details will be sent by email to those who are eligible. MRS Advances publishes snapshots of work in progress on key materials topics identified by MRS meeting programming. The journal is indexed in the Web of Science, Emerging Sources Citation Index, Scopus, and Scimago. MRS Advances offers rapid review and time to publication, and papers cited count toward the author's H-index. Don't delay. Submit your manuscript to MRS Advances before the January 3rd deadline.
Thank you to our 2021 MRS Fall Meeting Symposium supporters. Your support of a symposium session helps symposium organizers provide a high-quality technical program and encourages participation from researchers from around the world. Visit the MRS website to learn more about the MRS Symposium Support Program and how you can share in the Society's commitment to the advancement of scientific research.
In 2021, MRS Bulletin launched MRS Bulletin Impact, a premier outlet for high-impact original materials research. Suitable original research articles feature hot topics, innovative work, and foundational contributions. Learn more about submitting a manuscript at mrs.org/bulletinimpact.
The MRS On Demand webinar series offers an opportunity to learn about cutting-edge topics while networking with other researchers from around the globe. We invite you to join us in December for a series of government funding opportunity sessions. Visit mrs.org/webinars for a full listing of upcoming dates and topics.
It's not too late to submit an abstract for the 2022 MRS Spring Meeting. Late News Hot Topic abstracts will be accepted from December 16th to January 5th. Be sure to submit your abstract and join us in Honolulu for a perfect week of sun, scenery, and science. Pre-registration opens in January. We hope to see you there. Your opinion matters. Please take a minute during this very busy week to answer 3 quick questions about the 2021 MRS Fall Meeting. Use the MRS Meeting app to find the attendee satisfaction poll under the More menu. The poll closes Thursday evening.